Hello. Again, first of all, my name is Professor Lajimi, and you see the info on the screen. This course is an introduction to multivariable control. Um, um, the lecture number is on the video. So, and you see the contact information on the screen. Let's quickly go to page, I think it was 129. And let me I think I made a mistake when I was talking. I misspoke, and so just to recall, just to remind you, I think I said VH is the just to recall, just to correct it and say it in correct way. VH was, so starting from the right is singular value decomposition. VH was how we rotated the input directions, and then we had this sigma, which was the matrix of sigma. So capital sigma is the matrix of sigmas, and sigmas were the gain from one um, input to output, or the ratio of output to input. And then U was, in fact, the rotation that it would eventually. So once we had the VH, so we have rotated input, then we had the sigma, which describes, to remind you, the sigma, the matrix sigma, would describe how much it would the result of rotation after we rotated the input directions, how much we need to amplify or attenuate that result. And then U was the eventual rotation to essentially adjust the direction to align with output directions. So that's about that. And now I think we were here. So I've just updated some of the slides. So I'm gonna go start with simple SISO performance, what you already know, and then I've added some text to what we had. So if we start with this simple SISO performance, what you already know, let's assume we are going to control the speed of a single motor. This is, this is a real world example. We're going to control the speed of a single motor in, or a basic thermostat. In SISO, the sensitivity function tells us how well the system tracks a reference signal. So you turn the knob, which is your reference, and then the S tells us how much it would, how well the system would track my reference, how well the system tracks the reference signal or reject disturbances. For example, we have E omega equals S J omega equal R omega, where E is the error. Error is the difference between what we want and what we actually get. And R is the reference, your target, and omega is the frequency. For example, the speed of change. For example, how slow, for example, slow is fast vibration. Um, let's think about it this way. If S is a small, or I can just go back and then explain here, and then we're gonna see the description on the next page. So if S is a small, let's say close to zero, at low frequencies, where we have slow changes like gradual temperature shifts, tracking is good. And that makes sense if the change occurs very slowly. The system has sorry, an easier time to adjust to the tracking, to the reference, to your desired reference. Tracking is good, the system follows closely, and that makes sense, right? But why a small s? It means, sorry, it means less leakage of errors, most disturbances, in other words, most disturbances are corrected. Let's consider the simplified analogy. Imagine a bike with one brake. If sensitivity is low, a small bump doesn't throw you off much, right? So if sensitivity is low, a small bump doesn't throw you off much. And that matches your experience in reality. Is the same thing. If sensitivity is low, if sensitivity was high, even a small bump would throw you off a lot. Let's think about one more real world example from mechanical engineering. Think of a simple cruise control in a car. If a hill, a disturbance tries to slow you down, a small s means the engine quickly adjusts, keeping the speed steady. But if s is large, you feel the slowdown. All right? The system is super sensitive, and then s is large, and quickly the disturbance would translate into what you feel, and that means poor performance. Another example: a spring damper is in a bike suspension. Low s smoothes out the slow road bumps. Again, another example: consider a single spring damper in a bike suspension. So mountain bikes have have suspension, and for those suspension, low s smoothes out slow road bumps. So if s was large, then you would definitely feel even a slow road bumps. Um, so let me recap what I just said, just sum up this slide. Low frequency disturbance rejection and tracking rely on small sensitivity. So just to make it clear, S here is the error transfer function. It tells us how much of the reference slash disturbance leaks into error. Right? This is exactly the definition we see here. Let's go to MIMO now. In MIMO systems, like controlling an airplane with multiple flaps and engines, an airplane has multiple flaps and engines, or a car with four-wheel steering, things get more complex. We have vectors, lists of values for references, and errors to measure performance. I apologize. So again, let me just repeat what I just said. So we have, for MIMO systems, as you recall, we have vectors. We have vectors for references, and we have vectors for errors. So the vector of error is E omega, and vector of references is R omega. In MIMO systems, to measure performance, we use the vector 2 norm, which is like the total length or energy of the error vector. This so we have vector 2 norm of E omega over vector 2 norm of R omega, the reference vector, and the ratio of these two. This gives one number because we have vector 2 norms, and this gives definitely one number, summarizing to total error across all outputs, no matter how many there are, right? So why a 2 norm? Why a norm? Because with multiple outputs, speed, direction, height in a drone, you need a single metric to say overall how bad the error is the error. It's like adding up all shakes in a multi-part machine. All right. Sorry, I just saw this. I needed to fix this. And then let's take a look at the simplified explanation. The 2 norm is a root square of sums. Like for vectors, you can think of them as the energy associated with that vector, or it resembles energy, and it translates a vector or turns a vector into a single scalar number. But why this matters, the 2 norm doesn't change if you rotate the coordinate system, and it makes sense because the 2 norm talks about the magnitude of a vector. If you rotate the coordinate system, that doesn't change the magnitude of a vector. So it's reliable and fair. All right, it's fair because as you rotate the coordinate system, you can still compare the magnitudes. Consider this example in a two-wheel bike. Error in left and right wheels combined gives total wobble, meaning that if you think about it this way, so if you have error in your left and right wheels, then if each of them has an error, then these errors might result in a larger error, or they might somehow tend to not that correct each other, but it might result in a sum that's different. That describes the total wobble of your bicycle. Sorry, sometimes I'm not able to explain it properly, but I'm gonna think about it, and maybe I'm gonna come back with a with a more clearer explanation and description. So, but just to sum up, with multiple outputs, we need one number to summarize total error. Many real systems use weighted norms because units are different, but 2 norm is the standard starting point. 2 norm is a standard starting point, and then we can turn that into weighted 2 norm or something like that, just to adjust for the difference in units. So just to recap again, if I rotate the coordinate system of outputs, the 2 norm gives the same magnitude. This makes it a clean performance metric. Now let's see how direction matters in MIMO. Since E was equal to SR and S was the error transfer function, the gain error was equal to sensitivity matrix time reference, the gain, how much error you get, depends on the direction of R, right? So again, we are still in MIMO, right? So we have to always remember that the error also depends on the direction of R. Directions are like different ways to combine inputs. For example, pushing all engines together vs in other words, pushing all engines in sync vs pushing one engine forward and one backward. Sorry. Using singular values, think of them as the stretch factors. We have already talked about that. That sigma matrix in the middle was describing and does describe stretching or shrinking of the matrix S in different directions, like how a rubber sheet stretches unevenly. So we have this relationship, the vector 2 norm E over vector 2 norm R is between sigmas. Again, singular values, the sigmas, are like stretch factors. They have a minimum and they have a maximum. So the vector 2 norm, in this case, the vector 2 norm of E to R, remember again, S was the matrix, the error transfer matrix. This error transfer matrix essentially takes reference vector to error vector. And again, the vector 2 norm of error vector over vector 2 norm of reference vector is between the sigma, the minimum sigma, sigma underscore, and maximum sigma, sigma over bar or sigma bar. And the sigmas are the sigmas of matrix S at j omega or evaluated at j omega. Well, so sigma is the smallest singular value, weakest stretch direction, and sigma bar or sigma over bar is the largest, strongest stretch direction. And that makes sense because this vector 2 norm error or vector 2 norm reference, in some direction it would be strongly amplified, and in some direction it would be significantly attenuated. So if we had this minimum and maximum, then the ratio of vector 2 norm E omega over vector 2 norm R would always be between minimum and maximum sigma, between weakest stretch direction and the strongest stretch direction. Let's go through it again step by step. For the same input size, different directions give error between minimum and maximum singular value. And that also, besides math, that physically makes sense. For the same input size, different directions give error between min and max singular values. Same reference size but different direction, then you get different error sizes. Again, it makes sense. That's MIMO system, so you have to get different error sizes. They might be equal, but not there's no guarantees to get equal error sizes. A simplified, let's think about this simplified analogy. Pushing a table easy along the lengths, strong direction, and hard diagonally, right? So you might apply same input, same force with unit same force, force of the same size, let's say 1 Newton. But this 1 might be along y direction. Let's assume the length is along y direction. But then applying same 1 Newton force along the diagonal of the table, and that would be harder because that's a weaker direction, and that's the weak direction while the length is a strong direction. Let's think about engineering meaning of this statement. Bar sigma shows the worst case amplification. If a disturbance hits your system's weakest spot, how bad can it get? This is like designing a bridge. You care about the maximum stress under the worst wind direction, right? And you want to be sure that your design always consider this worst case scenario, meaning that whatever the worst wind direction is, you want to consider the maximum stress under that. In other words, think about it this way. If I consider maximum stress on the nicest wind direction, the wind direction that inherently creates maximum stress among all wind directions, I haven't really designed considering acceptable safety margins and safety criteria. Another example, in a robotic arm with two joints moving both in sync, easy direction, tracks perfectly, but opposing motions, hard direction, could cause wobbles or delays. So if we have same reference magnitude but different directions, always get different errors. So some means that for example, some command combinations are easy to track, others are hard, weak directions. Worst case means if nature chooses the most damaging direction, like wind direction, the most damaging directions, how bad can error get? How bad can maximum stress get? And this is essentially the robustness minus. Okay. Let's talk about performance requirements. Performance requirements are keep errors small everywhere. That makes sense. We want to keep errors small everywhere. To ensure good performance for all possible reference directions, you can predict them. You need sigma bar as j omega small, especially at low frequencies. Right? Because again, sigma bar was the worst case scenario, and the worst case scenario for your S, which was transfer function from reference to error, and it needs to be small because, just to remind you again, having a sigma small means that disturbances can be smoothed out, especially at low frequencies. But why we care about all directions, real disturbances? Because again, real world example, that bridge example, previous slide, because in real world, real disturbances aren't polite. The wind gusts are aircraft hit from any angle, not just easy ones. Easy meaning that the angle that's the easiest to control or the easiest to smooth out. It's like testing a car on all road types, not just straight highways. So that's what we are going to do. When we design the car, we're going to test them for, let's say, off-road cars. We're not going to design them for highways. We're not going to even design them for small angle, small slope, but then paved way, paved road, but rather we're going to test them on actual unpaved roads with twists, and then not as straight roads, not as straight off roads. Another example, if you consider quadcopter drone, if sigma bar is large, a side wind bad direction could flip it, right? If sigma bar is large, a side wind could flip it. Even if it's straight up hovers work fine. That doesn't mean if you have a side wind, it would work. A side wind, if you had designed the system with a large sigma bar, the side wind could easily flip it. Another example, in a bike with front/rear brakes, unbalanced sensitivity means skidding on turns. So in other words, let me just add one more thing here. You don't get to assume the reference is aligned with your favorite axis, the axis that you can control easily. It's not up to you. You don't get to assume. In real world example, you don't get to assume the reference is aligned with your favorite axis. Another example, as we just said, aircraft gusts do not, the sudden wind do not align neatly with roll-only, pitch-only directions. If it was aligned with roll-only or pitch-only directions, then you had the chance to easily counteract that disturbance. Let's talk about performance weight. We use a performance weight to define WPJ, to define requirements. It works like this: 1 over WPJ, the magnitude of WPJ. Again, we are always talking about, we have the magnitude of WPJ because, again, we're going to have the a vector, so it makes sense. It only makes sense to talk about the magnitude of the vector. But this vector is 1 over WPJ, performance weight, as the ratio of E over R. Again, vector to norm, vector to norm. Remind me, what was the ratio? What was this ratio? The ratio of the vector to norm, error vector to norm, and reference vector to norm. It was between the sigma underscore Sj, Sj omega, and sigma bar Sj omega. At low frequencies, what we do is, at low frequencies, we make WP large, so allowable error is tiny. This means tight specs. tight specifications for slow and steady tracking. At high frequencies, we relax it. You can't control super fast changes perfectly because at when we go to super fast changes, we need to essentially adjust our expectation to what we can achieve. So step by step, again, let me go through it step by step. WP is like a tolerance curve of where frequency is strict where it matters, lose it where it doesn't. And why wait? Again, this maximum allowable thing that we see here, we know the upper limit and lower limit of this ratio. You already know that. But then we think about it this way, that this is the minimum maximum, but where should we land between these two, between sigma underscore and sigma bar? So why weights? They turn vague specs like track accurately below 1 radian per second, ignore above 100 radians per second into math. Example, in vehicle suspension, low frequency bumps, potholes need a strong rejection. But high frequency vibrations like engine hum are okay to pass through a bit because we cannot in reality achieve a full, we cannot in reality we cannot fully reject that high frequency vibration. Another analogy is like speed limits. Low in school zones, critical, but high on highways, right? So we need to adjust. Sorry, occasionally I need to, I see something in my slides and I want to make sure that I don't forget to fix them. Okay. So let me sum up what I just said. A weight is a frequency dependent requirement. Makes sense because, again, go back to the definition. Weight was, go back here, it was 1 over maximum allowable, the weight itself, 1 over maximum allowable reference vector to norm error over reference to norm, or reference to norm over error to norm. So that was the definition of weight. A weight is, and it was, if you recall here, we have omega here, so omega, and we have to have omega because we're talking about certain frequency at which we define this error, vector to norm error and reference to norm error. A weight is a frequency dependent requirement. Low frequency demands a small error, tight tolerance. We need to be able to fully reject disturbances at low frequencies. At high frequencies, there's a difference. There's a different story. We need to think about, for example, that high frequency vibrations in a car, which is the result of engine hum, are okay to pass through a bit. So the key frequency domain condition for good performance, we have 1 over, and this is not again something new because we already know that this is equal to the ratio of error vector to norm and reference vector to norm, and this error vector to norm over error over reference vector to norm is always larger than a sigma minimum, and it's less than a sigma maximum. Sorry. So for a good performance, sigma bar S j, again S was the transfer function between the reference vector and the error, sorry, the reference vector and the error vector. Then for a good performance we should have this inequality, and 1 over weight, the magnitude of weight, has to be larger than sigma bar Sj omega, and this means that sigma weight multiplying Sj omega less than 1. This is essentially like shaping a system's response to stay on the curve. But in MIMO, we're doing that using singular values. This is what we do. So multiply S by WP and check if max singular value is under 1 at every frequency. What it means is no matter the frequency or directions, your weighted error stays below 1, ensuring specs are met everywhere. It's like ensuring a car's shocks handle all road types without bottoming out, or a multi-arm robot picking objects. This ensures precise grabs regardless of arm angles. What else can I say here? You might hear they call this loop shaping in MIMO language. You're shaping singular values, not scalar magnitudes. Again, this makes sense, right? Because singular values describe the worst case scenario and the best case, nicest case scenario. And then what you care about is to shape this singular values. You want to make sure that the singular values are essentially in the range they have to be. And this should be independent of what direction the command comes in, no matter what frequency. Error must be within a spec. So no matter what the frequency is, no matter what the direction is. Either way, this sigma, again, sigma was your singular value, right? We just use a different notation. Sigma was singular value. This this multiplying S by W should essentially be always under 1 at every frequency. And if that's problematic in terms of thinking about weight, you can go back to the definition of weight, right? Definition of weight was 1 over magnitude weight equals to ratio vector to norm error over vector to norm reference, and it was maximum allowable vector to norm error over vector to norm reference. So the maximum allowable multiplying this transfer matrix should always be less than 1, right? Because the S itself was, if you go back to the definition of S, you can see why this has to be less than 1. Let me just briefly talk about this H infinity norm, the ultimate worst case measure. The H infinity norm is maximum sigma bar mj omega, and performance requires, we just had that, WP weight as norm infinity less than 1. It's a double worst case scenario, worst direction at each frequency, then worst frequency overall. Again, that makes sense because we have worst direction at each frequency, and we have the worst case frequency overall. Essentially, we go through all the problems we might have with this control system, and we pick the peak problem. So we choose the peak problem across all scenarios. And so why I use this, it captures real engineering robustness. In a wind turbine, for example, ensuring blades don't oscillate badly under varying wind speeds and directions. And another analogy for that is like the maximum load a bridge can take in any storm. So what else? Just one more thing. Let me think about it. So let me explain this simply. The H infinity is a two-layer worst case, meaning that we choose worst direction at each frequency. That's singular value. Again, if you go back to the definition of singular values, we are talking about singular values at each frequency. And then we choose worst, not we choose, we have to consider worst frequency overall, which is max over all omegas, all frequencies. This is exactly how robustness specs are set, essentially. All right. Now, let's talk about the typical behavior of sigma bar as j omega. What to expect? Low frequency sigma bar s is much less than 1, so which results in great tracking because this sigma bar s, which was the ratio of which relates to our weight and also relates to the ratio of vector 2 norm error over vector 2 norm tracking, and its s was again the transfer function between the reference vector and the error. So much less than 1, so it means great tracking, like precise robot positioning. At high frequency, at 5 frequency, this sigma bar s approaches 1, right? So first case it was much less than 1, but then at high frequency this one approaches 1, and this approaching 1 implies feedback weakens and errors pass through the plant. But why this happens? In real mechanical systems, as we talked before, are strictly proper. So loop gain, that is L j omega, again going back to the beginning of this chapter, we talked about L as being the loop gain, goes to 0 as omega goes to infinity due to physics. Physics means when omega goes to infinity, if you think about it as a spring mass, you can think about why and under what circumstances that omega goes to infinity. So when omega goes to infinity, then due to, for example, inertia, um, what happens is that fast changes can't be corrected, and S goes to I identity matrix. If you go back to the beginning of this course, beginning of this chapter, you can remember why this S goes to identity matrix, and it does go to identity matrix. For example, in a car's steering, slow turns track perfectly, but at super high speeds, high omega tires can't respond instantly, right? And you have already seen this physically at high speed. Um, Even slow turns are going to be hard at super high speed because tires can respond instantly. Another example, shaking a heavy machine, slow shakes can be damped. Fast ones shake through. Fast ones go through the systems. Okay, in other words, at high frequency we cannot fight physics. Actuators have bandwidth limits. Sensors have noise. Models break down. Um, so if loop gain dies at high frequency, that's what we just saw, as L j omega goes to 0. If loop gain dies at high frequency, feedback cannot correct fast fluctuations. And it makes sense because you need the loop gain, and if loop gain dies at high frequency, feedback cannot correct fast fluctuations. I'm just getting tired, but I want to finish a few other things. Let's go to the next slide. The peak in sigma bar S, a common bump, usually sigma bar S goes above 1 near the crossover frequency where feedback starts weakening, and that's the frequency that all the things is about to break down. And why? It's a trade-off. Pushing for better low frequency performance often worsens things around bandwidth limits. Right? It makes sense. Like over tightening a spring, it bounces more at certain speeds. At lower speeds it might work well, but then at higher speeds it bounces more at certain speeds. Another example, in a bike fork, too stiff for comfort means jolts at medium speeds. Again, there should be a trade-off, and there is a trade-off. We have to decide what works best for our system, for what we are looking after. So for example, in other words, you pay a price near bandwidth. This is the MIMO analog of Bode's sensitivity integral ideas. If you recall from Bode's diagram for SISO, you could see the same thing. So now let's define the bandwidths in MIMO the conservative way. Since directions vary, bandwidth is based on the worst case, where sigma bar crosses 0.7, and this 0.7, the cutoff frequency was exactly what you saw in SISO. By worst case, each direction has its own speed limit. We pick the slowest to be safe, and again, it makes sense. Although each direction has its own speed limit, we pick the slowest to be safe. For example, in a multi-link robot, some motions are fast, for example, elbow band. Others slow. Uh, Bandwidth is limited by the lowest. And again, it does make sense. In other words, speed is always set by the slowest member of the team of your system. In SISO, the bandwidth is clear. In MMO, each direction have a different apparent bandwidth, so we choose the conservative one, the worst case. Because otherwise we have more than one bandwidth, so we have to choose the worst case, the conservative one. We can't go with the largest. That doesn't make sense, right? We have to choose the most conservative one. 0.7, if you recall, corresponds to -3 decibel for magnitude, a standard engineering convention. Let's link that to sensitivity to loop gain. But I think we're going to stop at this slide, 149, and we are going to come back in the next video lecture. Thank you for your attention. See you soon.